Welcome to The Debate. Our discussion today really dives into the statistical trenches. We're exploring a foundational kind of battle, if you will, between mathematical ideals and, well, messy real-world data. We're focusing specifically on data distributions, really the contrast between the perfectly symmetric normal distribution, the one often called the most important continuous probability distribution, and the pervasive, often problematic reality of skewed distributions. So the central tension here is about statistical priorities, fundamentally. Should our analysis prioritize the, let's say, elegant and necessary normal framework? It's defined by just two powerful parameters, the mean mu and standard deviation sigma. Or must our immediate primary focus be on conceptual clarity, which means identifying and, frankly, mitigating the statistical dangers posed by all this real-world skewness?
My position is that the normal framework provides the essential mathematical structure. It's the indispensable prerequisite for any higher-level analysis.
I see it rather differently. Look, I absolutely acknowledge the mathematical beauty of the Gaussian curve, the bell curve. But I have to stress that if our goal is descriptive accuracy and making robust decisions based on data, then conceptual vigilance has to prioritize recognizing skewness first. Failing to identify and account for that asymmetry, well, that's probably the single biggest statistical pitfall. It leads to conclusions that aren't just imprecise, they can be flatly misleading, especially when we're talking about critical data sets like, say, wealth or resource consumption.
Okay, but the normal distribution, the bell curve, it's indispensable precisely because it's simple, symmetric, and robust in many natural processes. It appears pretty reliably in phenomena governed by chance and averages. Think human height, measurement errors, IQ scores. Its power, as I said, lies in being entirely defined by just mu and sigma. And this structure allows us to move instantly from just raw numbers to actionable probability through standardization. Think about the z-score standardization for a moment. Z equals x minus mu divided by sigma. This doesn't just describe a point, it standardizes it. It lets us compare performances across completely different distributions, like comparing a score on a physics test to one on a history exam. This whole analytical infrastructure, rooted entirely in the normal framework, allows statisticians to generalize findings much more broadly.
That's a compelling point for mathematical generalization, sure. But it really sidesteps the risk inherent in that generalization, doesn't it? While the normal distribution is a wonderful ideal, assuming it applies in critical real-world applications is, well, it's often labeled the common mistake to avoid for a reason. Most high-stakes data things like income, house prices, biological lifespans, they are inherently asymmetric. They're skewed. And the critical statistical danger here, the thing we have to watch out for, is that in skewed data, the mean, mu, becomes dangerously misleading. It's mechanically pulled toward the long tail by extreme high or low values. Let's just stick with the classic example, income. It's heavily right-skewed typically. So if a company claims an average salary mu of, say, $100,000, that figure might be seriously inflated by just a handful of executives earning $500,000 or more. The median salary, however, the point where 50% earned more and 50% earned less, might actually be only $50,000. In that case, most people are earning far less than the proclaimed average. Prioritizing the mean here is it's a failure of descriptive accuracy. So if our goal is robust policy or just accurate descriptive analysis, say, informing tax policy or understanding how wealth is really distributed, the mean is fundamentally flawed when significant skewness exists. The median's robustness is its great strength. It's basically impervious to those massive outliers that drag the mean towards the tail. For datasets common in economics or real estate where huge disparities exist, the median is demonstrably the superior descriptor of a typical value.
Okay, I absolutely see why you emphasize the descriptive utility of the median, especially when we're discussing policy outcomes like wealth disparity. The median certainly offers a more stable picture of central tendency in that specific skewed context. I grant that. However, defining a distribution mathematically, that really requires the mean. If we just abandon mu and sigma for basic description, we kind of lose the context needed for higher-level mathematical modeling and, importantly, statistical inference. And maybe more critically, the mean is what allows us to precisely define the direction and the degree of the asymmetry itself. We establish skewness by examining the relationship. Is the mean pulled to the right of the median or to the left? Knowing that, say, the mode is greater than the median, which is greater than the mean, that immediately tells us we have left-skewed data.
Without calculating the mean, we lose that structural anchor, the reference point needed to actually quantify the asymmetry we're trying to describe. We need mu not just to find a center, but to understand the shape relative to that center.
That reliance on the mean for modeling is compelling. I see the logic. But doesn't that inherently require us to, clean up or transform the data first? Aren't we thereby already admitting the descriptive limitations of the mean for the raw data? I mean, if the standard statistical description of a town's housing market uses the median price, which it almost universally does, it's precisely because reporting the mean would give a false impression of what a prospective buyer could actually afford, all thanks to a few multi-million-dollar outliers. Let's call it the descriptive lie inherent in the mean, requires correction before any of that advanced modeling can even begin.
But that correction, or transformation, as you say, is exactly where the normal framework proves its enduring power, which maybe we can get into more later. Let me just circle back quickly to the concept of spread. I want to defend the empirical rule, the 68, 95, 99.7 rule. It is arguably the most useful initial tool for probability estimation when normality is established or at least assumed for basic instruction. It gives immediate, actionable insights into spread relative to the mean. If we teach the empirical rule, we're giving analysts a foundational insight. Knowing the standard deviation instantly tells you where the vast majority of the data likely lies. It's a powerful shortcut, really. And that ability to immediately assess variability relative to the center is fundamental to risk assessment and just initial data exploration.
I'm sorry, but I don't quite buy that premise, because teaching the empirical rule in isolation or encouraging people to apply it loosely, it just breeds carelessness. The risk of error, I believe, outweighs the initial ease of calculation when we're dealing with non-Gaussian data. The rule is strictly dependent on the data being normal. If we incorrectly apply the 95% rule to, say, highly left-skewed age-at-death data, where most of the data points are clustered near the maximum lifespan, the boundaries we generate would be completely meaningless. You could calculate a range that includes negative ages or biologically impossible ages, precisely because that core assumption of symmetry is violated. The pedagogical danger is very real. Students and even professionals can become so comfortable with this simple calculation of mean plus or minus 2 standard deviations that they just skip the verification step. And if the data is skewed, the standard deviation itself is distorted by the very outliers that created the skew in the first place. Since sigma squares the deviations, those extreme values have a disproportionate effect, often making sigma an overestimation of the typical spread around the center.
That's a strong point regarding the fragility of the standard deviation when dealing with extreme outliers. I do acknowledge that the reliance on sigma assumes a symmetric, sort of predictable spread of deviations around the mean. Yes.
Exactly. And that leads directly to the question of robust alternatives. When faced with heavily skewed data, what do statisticians instinctively do? They often abandon sigma and report the interquartile range, the IQR. The IQR, the range containing the middle 50% of the data, is a far superior, much more robust measure of spread for skewed data. Why? Because it's based on ranks and quartiles, entirely ignoring the extreme 25% on either side. It describes spread without being corrupted by the tail. So doesn't the very existence of the IQR as the kind of default alternative to sigma for skewed data suggest we must conceptually prioritize non-normal methods whenever asymmetry is identified?
I agree. The IQR is necessary when we are strictly describing the spread of non-normal data robustly. Absolutely. But that doesn't necessitate abandoning the normal framework, conceptually, in my view. It simply means we're choosing the most appropriate descriptive statistic for that specific task at that moment. But statistical analysis is about more than just description, right? It's about inference, hypothesis testing, prediction.
And many of our most powerful statistical tools, think ANOVA or inference and linear regression, they assume an underlying normal distribution of errors. Which brings us actually to the alternative solution you mentioned earlier regarding skewness, data transformation. For a heavy right skew, like say global wealth data, it's common practice to apply a log transformation. This action, I'd argue, demonstrates the enduring power and necessity of the normal framework. We don't just abandon it, we massage the data to fit it.
Okay. Tell me more about why you see transformation as a defense of normality rather than an admission of defeat. If we have to mathematically pre-process the raw numbers, going from dollars to the logarithm of dollars, haven't we already basically admitted the Gaussian model can't handle the raw reality?
We're leveraging its utility, I'd say. The log transformation in particular is powerful because it directly addresses the multiplicative nature common to skewed data like income or population growth. When income grows, it often grows by a percentage, right? That's multiplicative, not an absolute dollar amount, which would be additive. Logarithms convert those multiplicative relationships into additive ones. This simultaneously pulls that long, high tail closer to the center, compresses the spread at the upper end, and crucially, stabilizes the variance. The result is approximate normality. We are intentionally modifying the scale of the variable so that the advanced, powerful statistical tests that do rely on the Gaussian model can still be applied. We retain the utility of mu and sigma for inference, which is often the ultimate goal.
That's a highly sophisticated use of the framework, and I absolutely acknowledge that transformation allows us to use sophisticated parametric tests. However, it introduces a new layer of descriptive complexity, doesn't it? Once you analyze the log of income, your results, your means, your standard deviations, they're reported in log units. When you try to reinterpret those results back into real-world dollars for, say, a manager or the public, the interpretation becomes nonlinear and, frankly, much harder for a non-specialist audience to grasp. You've achieved mathematical rigor, sure, but perhaps at the cost of descriptive transparency, whereas if we were to abandon the parametric tests entirely and move to non-parametric methods which rely on ranks and medians rather than means, we can conduct valid inference without assuming or forcing normality. And this method is often preferred in fields like clinical trials or ecological studies, especially when data is ordinal or just heavily skewed and transformation is either infeasible or just too complex to interpret meaningfully.
Well, I still maintain that the normal distribution provides the critical mathematical structure and the standardized tools, z-scores, the empirical rule, and indeed, the basis for necessary transformations that are really the cornerstone of rigorous statistical work. Understanding its properties, how mu and sigma define it, and the techniques we use to approximate it, that, for me, remains the indispensable first step in moving beyond basic counting to sophisticated modeling. The flexibility inherent in the normal model, including transformation, allows us to, in a sense, conquer complexity.
And I'll conclude by just re-emphasizing the necessity of intellectual vigilance and maybe descriptive humility. While the normal model is undoubtedly a powerful theoretical concept, the most crucial takeaway for anyone interpreting real-world data is the ability to immediately identify skewness, often just by observing the often divergent positions of the mean, median, and mode. And then we must responsibly choose the most representative measure of central tendency and spread for the question at hand. For common, high-impact scenarios like wealth or housing prices, the descriptive risk you accept by relying solely on the mean, especially for initial analysis, they just seem to far outweigh the technical benefit.
I do acknowledge the descriptive risk you highlight, particularly for those kinds of distributions, and the clear importance of the IQR and the median in those specific contexts. Yes.
Ultimately, I think we both agree that the essential task always is to first examine the data and understand its true shape, because the morphology, the shape of any distribution, dictates the appropriate statistical methodology, which just underscores the absolute importance of diagnostic verification before proceeding with any analysis.